Assalamu alaikum. So today I will start with chapter 5, which is the discrete time stability analysis. And let's start with the following block diagram. Let's assume this is the input R of S. Here we have a sampler which has a sampling period of t. Let's assume here we have a G of S, and this is the Y of S. Let's assume here we have a feedback, and here we have H of S, and this is a negative feedback. Now from our previous lecture, we know that we can find Y of Z to be equal G of Z R of Z over 1 plus H G of Z. Now this is the closed loop pulse transfer function, which can be written in terms of the zeros and the pulse as certain constant k, the multiplication from I equal to 1 up to m. Here I'm assuming I'm having m zeros, z minus z of I over the multiplication from j equal to 1 up to n, the order of the system, which is the number of the poles, z minus p of j, multiplied by the input, which is the r of z. So here z equal z of I is the 0 of the pulse transfer function, and from here z is equal p of j, or the poles of the transfer function. So simply, now we can say that y over r, which will equal g of z over 1 plus h g of z. Now 1 plus h g of z equal to 0 is called the characteristic equation. Why call it the characteristic equation? Because simply this equation will decide the poles, and it will characterize all the performance of the system, such that the stability later on, when we study the time response, it will decide the rising time, the settling time, the percent overshoot, and so on, if we map those continuous time characteristic to a discrete time characteristic. So we need to study the stability, and we know that the solution of the characteristic equation will give me the poles. And from our previous lecture, we know that there's a relation between the S plane and the Z plane. So if we recall, we know that the relation between the Z and the S is the Z equal exponential of TS. And we know that S is a complex variable, so it can be written as sigma plus j omega d. So simply this means that Z is equal exponential of T sigma plus j omega d. So this can be written as exponential of sigma t multiplied by exponential of j omega d t, which has amplitude and angle. So simply, if this is the S-plane, this is the sigma, this is the j omega, and let's assume that this is the z-plane, so this is the real part and this is the imaginary part. So this is the S-plane and this is the z-plane. Now the imaginary axis, which is the boundary of the stability, we know that to the left of this axis the system is stable. To the right of this axis the system is unstable. So the j omega axis, this means that sigma is equal to 0. At the j omega axis, this means that sigma is equal to 0. So this implies that the amplitude of the z is equal to 1. So now the j omega axis is mapped to be a unit circle. So this is the unit circle which map the j omega axis. Now if we are in the left to the j omega axis, this means that sigma is less than 0. So this means that the amplitude of the z will be less than 1. So now the left half side of the S-plane will be mapped inside the unit circle, and in the right half side, which implies that sigma is greater than 0, which mapped to be the amplitude of the z is greater than 1, which mapped to be outside the unit circle. So simply, if I need to check the stability, someone will say, if I can find the exact location of the roots of the characteristic equation, which is here 1 plus gh of z equal to 0, if we can find the z's, the poles, which equal z of j, if those located inside the unit circle, the system will be stable. If at least one poles located outside the unit circle, then the system will become unstable. If we have a simple root on the j omega axis, which is mapped to be on the unit circle, so if we have a simple root on the unit circle, then the system will be critical stable. So let's highlight it here. Let's consider the following example. Let's assume that we have systems in the z domain, and let's plot the unit circle. The first one here, another system here, another one here, let's make 6 systems. And I'm plotting here the unit circle. Now this is the real part, this is the imaginary part for all the plots here. So the first example, let's assume that we have the following location of the roots of the characteristic equation. The second example, let's assume we have the following location. The third example, let's assume we have the following location. Here, let's assume we have the following location. And here, let's assume that we have the following location. And here, let's assume that we have the following location. Now here the cross indicate the location of the roots of the characteristic equation. So x here indicate the location of the roots of the characteristic equation. So the first thing here, system 1 is third order. Why? Because I'm having 3 poles, so the system is third order and equal to 3. Now all the roots are within the unit circle, so the system is stable. So all the roots of the characteristic equation are located inside the unit circle, so the system is stable. So system 1 is stable. Now what about system 2? System 2 has a simple root on the unit circle. All the other roots are inside the unit circle. So simply this is the condition of critical stable or marginally stable. So because we have a simple root for system 2, which is a root on the unit circle, all the other roots are located inside the unit circle, so the system is critical stable or marginally stable. Now what about system 3? Now here we have a simple root because this is a complex, and you know that if a complex, I should have a complex conjugate. So here those are not multiple roots, those are a simple root located on the unit circle, so the system is also marginally stable. Now what about this system here? Now this system here has a multiple roots on the unit circle, so the system unstable. Multiple poles on the unit circle. Now what about this system? This system we have 2 roots located outside the unit circle. Even if all the other root is located inside, I don't care. So at least one root is located outside the circle, the system is unstable. So the system is unstable. We have 2 holes outside the unit circle. Now what about the last system? Now the last system also we have one root located outside one circle, so the system is unstable. So the stability of the system can be decided by knowing the location of the characteristic equation roots. Let's take the following example. Let's assume we have the following block diagram. Here, let's assume we have certain controller with again K. Here, let's assume we have a zero order hold 1 minus exponential of minus s over s, which means that t here is equal to 1. And after that, here we have the transfer function for the plant, which is 1 over s plus 1. And let's assume this is c of s, this is r of s, and let's assume we have a unity feedback. So h here is equal to 1. Now we know that the combination of the hold circuit with the plant transfer function, we can call it g of s. Now here we need to determine the stability of the system. Let's assume if k is given to be equal to 1. Now the first thing, we need to find the closed loop pulse transfer function, and we know that c of z over r of z will equal k is equal to 1, so it will be g of z over 1 plus g of z, and 1 plus g of z equal to 0 is the characteristic equation. So we need to find this equation, which is the characteristic equation. So the first thing, I need to find g of z. So g of z is 1 minus exponential minus t will equal 1 minus z minus 1, and I will do the z transform for g of p over s, which will be 1 over s plus 1. So this is the gp of s, and this is the zero order hold. Now you can use whatever method you need to find the z transform. Previously we used the method of residue, so simply g of z will equal 1 minus z minus 1 can be written as z minus 1 over z, and this one will equal z over z minus 1 squared minus 1 minus exponential minus 1 z over z minus 1 z minus exponential minus 1. Now if we simplify, we will get g of z will equal to z minus 0.368 minus 0.632 z plus 0.632 over z minus 1 multiplied by z minus 0.368. Now if we collect the terms, this will equal 0.368z plus 0.264 over z minus 1 multiplied by z minus 0.368. Now this is a rational function which will equal n of z over d of z. We know that the characteristic equation is 1 plus g of z equal to 0. So this can be written in terms of n and d as 1 plus n of z over d of z equal to 0. So our characteristic equation can be written as t of z plus n of z equal to 0. So this will equal z minus 1, z minus 0.368, this is the d, plus 0.368z plus 0.264 equal to 0. Now if we collect the terms, z square minus z plus 0.632 equal to 0 is our characteristic equation. So this is the characteristic equation. If we need to find the roots, here second order, so z1, 2 will equal minus b plus minus the square root of b square minus 4ac over 2a, under the assumption that I'm writing the characteristic equation as a z square plus bz plus c equal to 0. So if we do the math, we'll have z 1, 2 will equal 0.5 plus minus j 0.618. So simply, this means that the amplitude of the z is less than 1. So the system is stable. So someone will say, can I judge about the stability without finding the exact location of the characteristic equation? We know that we only need to know the relative location. If this is the real part, the imaginary part, and this is the unit circle. So if I need to judge about the stability, I need only to know the relative location. Is the roots of the characteristic equation are located inside the unit circle, or outside the unit circle, or on the unit circle? So this will be the topic of our next lecture, inshallah. Assalamu alaikum.